Today's lecture will be a continuation of yesterday's, and maybe I should start by just reminding you of a few of the things that happened yesterday, because we're going to need them today. So I'll spend a few minutes doing that. So some things to remember. First, some definitions. The two-point function was the sum over all n Cn of x, z to the n. So z you should think of as a positive parameter. Cn of x is the number of n-step self-avoiding walks that start at 0 and end at x, and the two-point function is the generating function. The term when n equals 0 is equal to 1 when x equals 0, and otherwise it's 0, and it's kind of a special term, and we like to extract it sometimes, and what's left over is hz of x. So hz of x is the same as g, except the term with n equals 0 has been omitted, and it's written explicitly there as that delta. So this was kind of a key quantity that we were studying, and another one was the bubble diagram, which is just the L2 norm squared of the two-point function. And we're going to be living in the Fourier world a lot, and so we can write this L2 norm squared also as the L2 norm squared of the Fourier transform of the two-point function, because Parseval's relation tells us that those are the same. So this is equal to the integral over the torus of the Fourier transform, which is just a multidimensional Fourier series of dk. That's a d-dimensional Lebesgue integral, which is normalized. Squared, thank you. Now our goal is to show that the critical bubble diagram is finite for two situations. For the nearest neighbor model, if D is large, quite large, and for the spread out model, so in the spread out model, the self-avoiding walk is allowed to take steps from its current location to any other location which is in the box of radius L centered at its current location. And L is a large number, so it's greater than some L naught, which depends on the dimension, and we want the dimension to be bigger than 4. The reason that this is our goal is because if we know that, we saw via some differential inequality that it implies that the critical exponent gamma is equal to 1 in the sense that the susceptibility is bounded above and below by multiples of 1 over 1 minus z over zc as z approaches the critical value zc, which is 1 over the connective constant. So this is a statement that the critical exponent gamma is equal to 1. And that's what we're interested in. So this is what we want to show today. Now, we also had the Lace expansion, which gave us an expression for Cn of x, and therefore for the two-point function, gz of x, and also for its Fourier transform. And I want to recall what that said. So we know the following things from yesterday, that gz hat of k can be written as 1 minus z times the cardinality of the step set. So this omega is, with vertical bars, is just the number of places that a step can go to from its current location. In the nearest neighbor model, it would be 2d. In the spread out model, it would be something like L to the d. Then there's this d hat of k, and then there's a pi hat z of k. So d hat of k is the Fourier transform of the one-step distribution for the underlying random walk model. For example, so d of x is, you can think about it as c1 of x divided by the cardinality. It's just the probability that an ordinary random walk would step from the origin to x in a single step. And for the nearest neighbor model, d hat of k is something very explicit. It's 1 over the dimension, sum over the components of k of the cosine of the component. And, well, for the spread out model, you can also write this in terms of a Dirichlet kernel. It's something very explicit that you can do any kind of calculation with that you want. And you can consider it to be completely understood. What's less understood is this pi, which is the generating function for that sequence pi m of y, which was counting the number of paths consisting of m steps that start at 0 and end at y and go through some kind of specific topology on the way. So I rewrote this as chi z inverse plus z omega times 1 minus d hat of k plus pi hat z0 minus pi hat zk. This was just a manipulation. There was nothing to this. It was just some algebra that was based on the fact that when k is equal to 0, the Fourier transform of the two-point function is the susceptibility. And by using that and just doing some arithmetic, we ended up with this expression. So what's happening as z goes to zc, you should think of it in this way, that this term is disappearing and becoming increasingly unimportant as z goes to zc. This is the main term, which is like the simple random walk two-point function, Fourier transform. And this is something that we need to figure out how it affects that simple random walk behavior. And we want to show, in fact, that it doesn't really have an effect, because what we're trying to do is to prove that the self-avoiding walk is behaving like the simple random walk in the sense that this critical exponent gamma is equal to 1, as it is for simple random walk. Okay, so we had this formula. And what was pi? Well, pi z of x was equal to the sum over n equals 1 to infinity minus 1 to the n of pi z n of x. So it was an alternating series. The pi z n of x is always non-negative. And this pi z n of x was a generating function for these paths with n loops that we saw last time. So pi z n of x was a generating function, sum over m from 2 to infinity of pi m n of x z to the m. So this quantity here was counting walks of a certain type. It's a non-negative integer. In fact, we don't need to know what this is anymore. All we need to know about it for today is the estimates that I mentioned at the end of yesterday. So that was a theorem. So this is I'm still recalling what happened yesterday. This was a theorem that said that for any z greater than 0, we have the following two bounds. One is a bound on the L1 norm of pi n z. First of all, it's non-negative by definition. And then the upper bound had two parts depending on the value of n. N equals 1 is a little bit special. And there the bound was z times omega times the L infinity norm of h. And for larger values of n, there's again an L infinity norm of h, and that's multiplied by the L infinity norm of the convolution of g and h to the power n minus 1. I also mentioned last time that in order to understand this, we really need to understand a sum. We really need to understand pi zn when it's multiplied by 1 minus the cosine of k dot x. And so we had a bound of the form sum over x, 1 minus cosine k dot x, pi zn of x. First of all, that's equal to 0 if n is equal to 1, because inside this pi 1, there's a delta function that forces 0 to x. This is where the self-avoiding returns. And so x is always equal to 0 when n is equal to 1. And so the cosine becomes cosine of 0, and there's a cancellation. For the upper bound, there's some factor that depends on n, polynomial factor that doesn't matter. N squared will do. You can do better. And then there's a L infinity norm of 1 minus cosine k dot x times hz times this same L infinity norm of the convolution to the power n minus 1 if n is greater than or equal to 2. So we had reached this point yesterday, and at that point I also mentioned that this convolution, this norm of the convolution that we're looking at here actually has something to do with the bubble diagram itself. Remember, our goal is to prove that the critical bubble diagram is finite. That's why we're doing all of this. And what I was saying at the end at last time was that these upper bounds that we've proved say something, have something to do with the bubble diagram. In fact, if you use the Schwarz inequality, then what you find is that the L infinity norm of a convolution, I mean, this is somebody's bound, Hausdorff-Young or something like that, is bounded above by the L2 norm of the product of the L2 norms of the factors that are being convolved. It's a special case of the Hausdorff-Young inequality, but it's just the Cauchy-Schwarz inequality as well. Write out the definition of the convolution and use Cauchy-Schwarz. This is what you get. Now, h is less than g. Right? Z is non-negative here, and h is less than g. It differs by that delta function. So we can always bound it above by g. And so this is bounded above by the L2 norm squared, which is the bubble diagram. So this is where I finished last time, and I sort of gave a bit of a despairing note to this conclusion, because I said that what we're trying to do is to prove that the bubble diagram is finite. We don't know that it's finite originally, of course. And so we've gone through all of this procedure. We found this pi of 0 minus pi of k that we want to absorb into this term. So we need estimates on it. We go and do the estimates, and we find in the end that what we really need to know about in order to control pi is that the bubble is small. And our goal is to prove that it's finite. So if we need to know that it's small in advance, we feel uneasy. So this is where I was last time, and now I'll start to do something new, but maybe I should just pause and ask if there's any questions at this point. Anything else that, yeah? I proved the n equals 2 case. Yeah, so if you wanted to prove the n equals 3 case, the diagram looks like this. And if you wanted to bound, let's say you wanted to prove this bound right here, then what you would do is first of all say, okay, inside this pi m3, I have configurations that look like this of length m with various avoidances between the lines in the diagram. I'll just forget about all of those avoidances, and that will give me an upper bound. And then effectively what I have when this is, so the contribution, if I just write pi 3 zx like that, then the contribution that I get will be the sum over y, which is the location of this vertex, of hz of y squared times hz of x minus y squared times gz of x. That's the kind of bound that you'll get. And then you just fool around with this bound. So I think I won't go through all of the steps, but I'll just draw you the picture. You can pull off an L infinity norm of h of y. So that will pull out the L infinity norm, worst case, which is this factor right here. And then you want to have two convolutions left over. Indeed, you'll have 4 factors of h and g left. You'll have one h left here 2 H's here and a G. That's 4 altogether. And the way that they're organized is like this. And the sums over these vertices correspond to convolutions, and it works out. So I leave it as an exercise to, or you can look at my Sam Fleur lectures where it's all written down in detail, which, by the way, are available on my webpage, so you can just download the whole book there. Are there any other questions? Okay, so I have said that it looks like we're stalled now, but what we'll do, there's an idea that we want to use here, which is that the self-avoiding walk, yes? I don't want to estimate pi z of x. I want to estimate pi z hat of k. And I'll use bounds like pi z hat of k is bounded above by the sum over x of pi z of x by just throwing away the exponential. And then I'll even throw away these minus signs and say that's bounded above by the sum over x and the sum over n of pi z n of x. And that's how we're going to use these. All right, so the idea is that we want to somehow capture our belief or expectation that the self-avoiding walk should be behaving like the simple random walk. And one expression of that might be the following. So we have to go all the way to the critical point. And so I want to say that this L2 norm here, which is also the L2 norm of the Fourier transform by Parseval's relation. So this is a sum over x, and this is an integral over k. This is also equal to gz hat minus 1, because the Fourier transform of the delta, the Kronecker delta there, is just 1, which is the difference between g and h. So the idea is that this should look like its simple random walk counterpart. That's what we want to try to exploit somehow. It should be small when its simple random walk counterpart is small. And that simple random walk counterpart is going to be what I'll call Cz of x, which is just the sum from n equals 0 to infinity of Cn0 of x, z to the n, where this Cn0 of x just counts the number of simple random walk paths that start at 0, end at x, and do that in n steps. So I want to argue that the self-avoiding walk bubble diagram, or at least the norm of h, should look like the corresponding thing for simple random walk. We'll have to prove that, but this is the way that we're heading. So the critical value for the simple random walk is not zc anymore. That's the self-avoiding walk critical value. The simple random walk critical value is actually smaller. I'll call it z0, which is 1 over the cardinality of the step set, because that C0 n of x is growing like this omega to the nth power for simple random walk. There's omega options at every step, and fixing it to end at x is not an issue. So if we take the Fourier transform of that C over there, what we end up with is Cz hat of k, and it's an easy computation. Actually, it's just this same computation, but without the pi term. It's just this part. So it's 1 over 1 minus z omega d hat of k. And you can see that the simple random walk susceptibility is what you get when you put k equals 0. It's just 1 over 1 minus z times omega. So at the critical point, Cz naught hat of k is 1 over 1 minus d hat of k. Because the z naught cancels the cardinality. So I want to argue, or I want to hope, that this norm of h should look like the corresponding quantity for simple random walk. So the simple random walk analog of hzc L2 norm squared, or put a hat on it if you like, will be like that, except replace g by c. So it's Cz naught hat minus 1 L2 norm squared. Now what is that? C hat is 1 over 1 minus d hat. If you subtract 1 from that, you end up with d hat over 1 minus d hat. So this becomes d hat over 1 minus d hat L2 norm squared, which is just the integral over minus pi pi to the d of d hat of k squared over 1 minus d hat of k squared dk over 2 pi to the d. Now d hat is something explicit. For the nearest neighbor model, it's that normalized sum of cosines over there. And so now it's a calculus problem to understand what this integral is doing. So here's the solution to the calculus problem, the proposition. Let the dimension be greater than 4. Then this integral, which I'll write in short form as d hat squared over 1 minus d hat squared, is less than or equal to beta, which is a small parameter that takes on different values according to which model we're talking about. This is the only place where you have to think about which model you're working with. For the nearest neighbor model, it's less than some constant over d minus 4. And for the spread out model, it's less than some constant over L to the d, or the cardinality of omega, for the spread out model. And so if d is very large in the nearest neighbor model, then this beta is as small as you want it to be. And if you're in the spread out model with dimension greater than 4, and you take L as large as you like, then again you can make this quantity as small as you want it to be. So this is encouraging, if it is indeed the case that the self-avoiding walk bubble is behaving like this simple random walk bubble, because then we're going to be able to get meaningful bounds out of these estimates that we have here on pi, in the sense that this quantity is going to be a small number, and we'll be able to do the sum over n and hopefully make some tracks. We're still in the situation where we need to know what we're trying to prove in order to advance, but at least we're getting some indication that it could be it's reasonable to think that it's true. So the proof of this is calculus. And I don't want to do the calculus, but maybe just give you some indication as to why it could be reasonable. First of all, why do you need d greater than 4? It's because of the behavior of the integrand near k equals 0. So d hat behaves like 1 near k equals 0. In fact, it behaves like 1 minus the norm of k squared. Right? If you just expand out the cosines in a Taylor series to second order, then this becomes 1 minus k squared. And the 1 is canceled by the 1 here. And in the numerator is like 1. So the integrand is behaving like 1 over k squared near k equals 0. And that will only be integrable if the dimension is greater than 4. Otherwise, the integral will be infinite. So that explains why this hypothesis is present. And now, why do you get something small? Well, just expand out d hat squared over 1 minus d hat squared in powers of d hat. And you'll get d hat squared plus, and so on, higher order terms, d hat to the 4th term, etc. I just want to look at the first term. When you do the integral, it's the integral of d hat squared, which is the same as d star d evaluated at 0. Okay, the Fourier transform of d star d is d hat squared, and we're evaluating here the inverse Fourier transform at 0 in this integral. So this is just d star d at 0, which is the probability that the underlying random walk takes a step away from 0 and then steps immediately back. And that integral is, that probability is just 1 over the number of possible steps, because the first step can do whatever it wants, and then the next step is constrained to reverse that first step. And so this is behaving like 1 over 2d for the nearest neighbor model. Well, it is 1 over 2d for the nearest neighbor model, and for the spread out model, it's some constant over L to the d as far as its large L behavior is concerned. So at least the first term is okay, and it's reproducing this behavior. You need to argue that the other terms don't create any mischief, and they don't. So you need to argue that this term dominates. Okay, so that's where the calculus comes in. Now, these integrals that are showing up here actually have some probabilistic meaning. If you were at the first tutorial on Monday, then problems 6 and 7 were related to this. So just a remark as to what these integrals involving 1 minus d hat actually mean. If we just looked at the integral of 1 over 1 minus d hat like this. So I'm leaving, the integral is over minus pi to the d, and it's with respect to the normalized Lebesgue measure on that torus. But what this is equal to, probabilistically, it's the expected number of returns, well, of visits to 0 for a random walk which has started at 0. And the fact that this integral only converges for d greater than 2 is the proof that the random walk is transient in dimensions greater than 2 and is current in dimensions 1 and 2. So there's these kind of integrals, they have some probabilistic content. And actually, if you look at the integral of the square of 1 over 1 minus d hat, then the probabilistic interpretation of this is that it's the expected number of intersections of 2 independent simple random walks that start at 0. Okay, infinitely long simple random walks started at 0. How many times do they intersect each other? On average, it's given exactly by this integral. And so in more than 4 dimensions, when this integral is finite, that expected number would be finite. And in 4 or fewer dimensions, on average, there are infinitely many intersections. So again, we're seeing the role of 4 dimensions popping out here. All right, so now I come to the main theorem for today, which is going to achieve our goal. So the theorem says that there's a beta naught greater than 0, very small number, such that whenever this inequality holds, when star holds for beta less than or equal to beta naught, then the critical bubble is less than 1 plus some constant times beta. Okay, so there exists some constant so that this will be true. So what it's saying is that whenever the simple random walk, this is not quite the bubble diagram. The bubble diagram would have a 1 here rather than a d hat squared in the numerator, but this is almost the same as the bubble diagram. Whenever it's small, then the self-avoiding walk bubble diagram is also small. So there's going to be some comparison between the two. And then as a corollary of this, we're done. So star, once we've verified that, which this proposition does verify for the two cases we're interested in, nearest neighbor model in high dimensions or spread out model above dimension 4, then we get gamma equals 1. All right, so for the nearest neighbor model in D large, or the spread out model for L large. And our goal will be achieved. So proving this theorem is enough. This proof of the theorem uses a lemma which you might find looks a bit strange at first. It's a trivial lemma, but it won't be immediately obvious how to use it. So it says the following. It's a first-year calculus lemma. Let A and B be real numbers with A less than B. Think of them as positive. Let F be a continuous function on the interval Z1 to Z2. This lemma's got nothing to do with self-avoiding walks at the moment. It's just a calculus fact. And suppose that F of Z1 is less than or equal to A. And here's the strange hypothesis. Suppose that you could show that for any Z which is strictly between Z1 and Z2, if f of z is less than or equal to b, then f of z is less than or equal to a. So if f of z is less than or equal to 4, then it has to actually be less than or equal to 3. Suppose you knew that. Then the conclusion is that f of z is less than or equal to a for all z in the interval z1 up to z2. Looks kind of silly, but it's extremely useful. So here's how the proof goes. Here's Z1 and Z2. Here's A and here's B. This is the graph of F. I know that F of Z1 is less than or equal to A. F is continuous, and I know that its graph is not allowed to enter this rectangle because if it did, then it would violate this hypothesis that when F is less than B, it's less than A. So that region's forbidden, and so the graph has to lie below it, and that's the end of the proof. It's the intermediate value theorem. This lemma has been used a lot in these place expansion arguments. It's a kind of replacement for induction, where you get to assume something that would be very useful for you in order to prove what it is that you want to prove. So let me tell you what our choice of F is. we have to make a very good choice of f. So I'll draw a picture. This is the z-axis here. And what I'm going to do is simultaneously draw the susceptibility for the simple random walk model, which underlies our self-avoiding walk model, and for the self-avoiding walk model. Now, the simple random walk model has critical value z0, and it blows up there. In fact, I mean, we know exactly what it is. It's just simply the function 1 over 1 minus z over z0. So it starts at 1, and maybe I'll draw it in red here. It blows up like this. So this is the function cz hat of 0. It's the susceptibility for simple random walk. Now, the self-avoiding walk, there are fewer self-avoiding walks, and so the radius of convergence is larger for the generating function. It's over here somewhere, zc. And it stays below this graph, and it blows up. And really, what we're talking about here for the last couple of days is to try to prove that this is blowing up linearly, which is the same way that this red curve is blowing up, because we know explicitly how that red curve is behaving. So what we're going to do is take a z that we're interested in here, which is going to be approaching zc, and that z is going to choose a partner that corresponds to simple random walk. It's going to say, you know, I want my 2-point function, my self-avoiding walk 2-point function, to be just like the simple random walk 2-point function for some value over here. And the way that I'm going to choose that value is by insisting that the susceptibilities be the same. So I'll go up like that, over, and then down here, and then I'm going to call this value p of z. And what I want to say is that this chi of z, which is gz hat of 0, this p of z has been chosen just so that the susceptibilities agree. But I hope that even more is the case, that not just the susceptibilities are the same, which is by construction, but that in fact the self-avoiding walk 2-point function over here should behave just like the simple random walk 2-point function over there. I'm going to build my choice of f with that hope, and ultimately in the proof we'll see that the hope is really realized. So in k-space, yeah. So for z in 0zc, we'll define p of z, which is in 0z0, by the formula gz hat of 0, which is just chi of z, should be equal to cp of z hat of 0, which is just 1 over 1 minus p of z times omega. That's the simple random walk 2-point function. Is an extremely trivial function. On the other hand, this chi, or g hat of 0, for that matter, is 1 minus z omega minus pi hat z reciprocal. So we can write a formula for this p in terms of pi. So if you do the arithmetic, what you find is that p times omega is 1 minus 1 over chi of z, which is, then the 1's cancel, and it's z omega plus pi hat z of 0. So I'm choosing p in that way. And then the idea is that you expect, or let's say that you hope, because it's possible that it wouldn't work, but you hope that for any k, not just for k equals 0, where we've chosen p so that things work out that the two susceptibilities agree, we'll hope that the Fourier transform of the 2-point functions are the same for all values of k. Not exactly the same, but close to each other. So that is that gz hat of k should be approximately equal to c hat pz of k. I'll make this more precise in a moment, but I'm just trying to motivate the definition of K, of F. And even more than that, so here's a last fact which I have to say just because I don't want to lie to you too much, but I don't want to dwell on it. So the other thing that we're going to hope is that 1/2 delta K gz hat of L is approximately equal to 1/2 delta K c hat pz of L, where I haven't defined what this delta is yet, but it's defined like this. This is equal to plus or minus. I don't guarantee I got the sign right here, but it's so L plus K. So this is the definition of it. It's a kind of derivative, in a way, of G. It's not exactly a derivative, but it's comparing the value of G hat at L with the values at K and minus K, the average of those two. And this is the Fourier transform with respect to L of 1 minus cosine K dot X G Z of X, which is something that I said that we needed to study. So, pardon me? Yeah, so I want this to be true for all K and for all L. Yeah, so I'm asking a lot. But it turns out that it's true. Okay, so this part I don't want to dwell on. It's more of a technicality than anything else, but it does enter at some point, and I'll tell you the point where it enters. Okay, so this was sort of motivation for how we're going to choose this function f. So first of all, z1 will be 0, z2 will be zc, b will be 4. 4 is a completely arbitrarily chosen number greater than 1. Okay. If you want it b to be 3 or 2, that would also be okay, or b equals 100 would be fine. And a is going to be 1 plus a constant times beta. And, well, the value of the constant will be determined later, but think of the constant as being equal to 100 or something like that. So that's the easy part. Now what about f? So we've got an a which is less than b. We've got a z1 and a z2. What I need is a continuous function f, and we'll have to verify that it obeys the hypotheses, and actually then to see why the lemma does the job that we want it to do, that is, that it proves this theorem. So f is going to be the minimum of 3 things, f1, f2, f3. Pardon? Maximum. I always do this. Where f1 of z is just equal to z times omega, this f1 is going to allow us to control the critical value. You see, the problem is that a priori, I mean, I guess we could use Keston's results if we wanted to, but we're trying to keep self-contained here and not make any assumptions on, a priori assumptions on how large ZC is compared to Z naught. We'd like it to come out of the proof. And this f1 is going to help us control that. f2 of z is equal to the supremum over all k in minus pi pi d of the ratio of gz hat of k and cpz hat of k. So saying that f2 is less than 4 is saying that g hat at z is less than c hat of p of z. So that's the sense in which we're assuming this approximate equality here in terms of an upper bound. And then there's another F3, which is the part that I prefer not to tell you about, but I have to say at least something. So it's the sup over all k and L of the ratio of these guys. So 1/2 delta k gz hat of L divided by 1/2 delta k cpz hat of L. And I wish it was that, but actually I'll put this in quotations because it's something else in sed, which is kind of like that. So there's some way of comparing these two things, which I don't want to go into details about because there are more interesting things to talk about. So the quotes mean it's something like that, but not exactly that. No, it's non-negative. Actually, it comes out of the proof that this one is non-negative as well. But this one's explicitly non-negative because we've got a formula for it. Put them there if you feel more comfortable. But you don't need them. All right. So we'll have to verify that this f obeys all of the hypotheses of the theorem, which weren't that many, actually. It has to be continuous. F of z1 has to be less than or equal to a. And then there was that big hypothesis that less than 4 implies less than a. But let's suppose that we do that. Then we could apply the conclusion of the lemma. Okay, so we still have some work to do in order to verify that we can, in fact, draw the conclusion from the lemma. We have to prove the hypotheses. But what the conclusion will tell us is that f of z, our f, will in fact be less than or equal to a for all z less than zc. So the conclusion of the lemma is that f of z is less than or equal to a, which for us is 1 plus order beta. That's the a that's going to be popping out here. For all z less than zc. Now, in particular, f2 of z will be less than or equal to a because f was the maximum. So f2 will be smaller. So in particular, f2 of z is less than or equal to a. So that says that for all k, gz hat of k is less than or equal to a times c hat pz of k. Now, the critical bubble diagram, which is what we're trying to show is finite, is equal to the limit as z increases to zc of the bubble diagram at z, which is the limit as z increases to zc of the L2 norm squared of gz hat. And so we can apply this inequality and see that it's less than or equal to a squared times the limit, no square, yeah, the limit as z approaches zc of the L2 norm squared of c pz hat. I'm just using this inequality inside the integral, which is given by the norm. And, well, this is equal to a squared times the limit as z approaches zc by Parseval of the same thing in x space. And this one is monotone. In fact, it's something very explicit. It's monotone. Well, it's monotone by definition. It's a power series with non-negative coefficients. And so this is less than or equal to cz naught. And cz naught, well, if we go back to K-space, this would be this thing. So essentially, the way the argument is going is it's saying if we have this inequality, then when we try to compute the bubble for z equals zc, we can back off a little bit with the limit, and then we'll have a p of z over here, which is subcritical for simple random walk. And, well, the bubble diagram, even at the critical point, is finite, so there's going to be no problem. Okay? And we'd be done. The goal is realized. So what remains to do is to show that actually this f obeys the hypotheses of the lemma. Have any questions? Yeah, but it's integrable. No, c hat at z naught is integrable, is infinite. But this is in x space, cz naught of x is finite for every x. That would be the expected number of visits to x by the simple random walk started at 0, which is finite. Any other questions? You can't read it, you mean? So you're okay here? Yeah, so what I did here was I had a c of p of z, and I'm taking the limit as z approaches zc. As that happens, p of z is going to z naught. And so I just replaced the p of z by z naught because this is monotone anyway. And then I said that the L2 norm in x space of c of z naught would be the L2 norm in k space. And the Fourier transform of c of z naught is just 1 over 1 minus d hat. And so I have to integrate 1 over 1 minus d hat squared. But that's finite because d is greater than 4. Okay, so now we have to verify that this f obeys this hypothesis of the strange lemma. So we check the hypotheses on f in the lemma. There were 3 hypotheses on f. Yes? I'm sorry, I can't hear you. I don't want to. I didn't try to. This is the right thing to use in this context precisely because this is the Fourier transform of this quantity, and this is the quantity that enters in the bounds on pi. And so this is what we have to analyze. We're working in the Fourier transform, so we want to look at its Fourier transform, and it is this. So this is what we study. So there were 3 hypotheses. There was the continuity. RF is continuous. You have to check each of the 3 bits. This one is linear in Z, so that I'll do that one. You can do the rest. As for the other ones, if you didn't have the supremum here, then these would be obviously this would obviously be continuous because we're talking about convergent power series. You have to worry a little bit about the supremum, but it's no problem. So I'll just say this is easy. Let's talk about the important things here. So the other second hypothesis was that f of z1 was less than or equal to a. Our z1 is 0. And a is something like a little bit bigger than 1. So we just go and check. and see whether that's the case. F1 at 0 is 0, so that works pretty well. F2 of 0, well, when z equals 0, this generating function is just the term, the first term, which is 1. And same thing in the denominator. When z equals 0, p of z is also equal to 0. If you remember my picture, z looked for its partner in the susceptibility, and those two curves came together at z equals 0, where they both had value 1. So, in fact, F2 of 0 is 1. F3 of 0, once you properly define these quotation marks, is equal to 0. So this also is something which is not problematic. It's the other hypothesis on F that is the significant one. So the difficult step, where you actually have to do some work, was that surprising hypothesis in the lemma. What we need to show is that for z between z1 and z2, which for us is 0 and zc, we have to show that if f is less than or equal to 4, then it's actually less than or equal to a, which is a little bit bigger than 1. Okay, so let me show you how that works. I'll just do it for F1 and F2, and I'll leave it to your imagination for F3. For F3, you don't really need any new ideas, but you need to write more stuff. Okay, so we assume this. This is like getting us started with an induction argument. We get to assume that, for example, F2 is less than or equal to 4, which means that we get to assume that g hat is less than 4 times c hat, which means, as we saw over here, that tells us actually that the bubble is finite. So our assumption is giving us what it is that we're trying to prove, that the bubble is finite. Of course, we have to prove that it's even more finite than we thought, because we have to get this a out. All right, so here's the proof that f1 of z is less than or equal to 1 plus order beta. Right? F consists of 3 parts. We have to prove that each one of those 3 parts is less than 1 plus order beta. So let's start with F1. Now, the susceptibility is non-negative. And we have to use the Lace expansion, right? So the Lace expansion gave us a formula for the reciprocal of the susceptibility. It gave us a formula for the reciprocal of the Fourier transform of the 2-point function, and when we put k equals 0, that's a susceptibility. So we have this formula, which is that chi z inverse, reciprocal, is 1 minus z omega minus pi hat z of 0, and that's positive. So f1 of z is this term here. We take it over to the other side. We get an upper bound on f1 of z. So f1 of z, which is z times omega, is less than 1 minus pi hat z of 0. So what we need to show now is that pi hat z of 0 is order beta. Then we will have drawn this conclusion, since a is 1 plus order beta, we will have drawn this conclusion for f1. Now, this comes back to Ron's question, why were we studying those sums over x's of pi n of x? It's because it gives us this bound on the Fourier transform. So fz is less than, or well, it's less than, but I'll write less than or equal to 1 plus, throw away the sign, And that's less than or equal to 1 plus the sum over x pi z of x. Right? The L infinity norm of the Fourier transform is bounded by the L1 norm in x space. I'm just throwing away the exponential. Take absolute values inside the sum that defines the Fourier transform. And then write this as 1 plus the sum over x, well, sum over n, and sum over x of pi z n of x. Pi z of x was an alternating sum of pi z n of x. Just throw away the minus signs. Now, substitute in the bound. We have bounds on this quantity that came from the theorem from yesterday in terms of g star h. You remember those? I recalled them at the beginning today. And so what we end up with is there was an L infinity norm of h inside the bound on pi n for every value of n. I pull that out. The value for n equals 1 was a little bit special. It had this factor. And then the other values for n equals 2 to infinity had gz star h infinity norm to the power n minus 1. So here I've applied the theorem. I haven't applied yet the hypothesis that f of z is less than or equal to 4. That hypothesis is quite helpful for this first term. That 4 can go into the constant in the O of beta. So for example, if I knew that this was order beta, then this term would be okay. And then I also need to control this infinite sum here. So we're going to need a bound on the L2 norm squared of h, because actually, well, we'll see why that's useful in a moment, I guess. In fact, I think before I do that, I want to make the observation that I've already made, that gz star h infinity is less than or equal to infinity norm of h plus the infinity norm of h star h, just because g itself is equal to the Kronecker delta plus h, and the Kronecker delta serves as the identity under convolution. And this is less than or equal to the infinity norm of h plus the L2 norm of h squared by Cauchy-Schwarz. We've already seen that more than once. So what we need to do to control this entire right-hand side is to bound the L infinity norm of h. That will also be an ingredient in understanding this sum, for which we'll also need the L2 norm. And so now I'm talking about the bound on the L2 norm. Now, the way that we benefit from the fact that h does not include the zero-step contribution of the two-point function, that's you see, we wouldn't want to have the delta inside here. We wouldn't want to have g instead of h, because this norm would be 1, and that would be no good. So we had to take it out, and the way that we benefit from that is by using subadditivity to say that if you take at least one step, then you go somewhere, and then forget about the fact that what you do afterwards has to avoid the initial step. Then this would give you a bound z omega d star gz of x. So this omega d is just canceling and giving you the number of one-step walks that go somewhere. And this is saying take a one-step walk somewhere and then do whatever you want after that. And don't worry about avoiding the origin anymore. So this then z omega can be bounded above by 4. And we have this inequality. So that bound by 4 is using the assumption that f of z is less than or equal to 4, in particular in the form that f1 of z should be less than or equal to 4. All right, so now if I want to bound this L2 norm squared, just use this inequality. That's less than 4 squared times the L2 norm of d star j. And now there's a bit of fooling around going back and forth between k space and x space in order to make use of monotonicity together with our assumption on F2, which is an assumption that says that the Fourier transform of G is bounded above by 4 times the Fourier transform of C at the adjusted value P of Z. So there's a bit of fooling around with that. And so the first step is to use Parseval's relation to rewrite things in K space, because that's where we get to use our assumption that F2 of Z is less than or equal to 4. That assumption says that this G hat here is actually bounded by 4 times C hat at P of Z. So we get another couple of 4s when we use that. Four to the power 4, yeah, 2 more, right, thank you. And, well, this is equal to 4 to the power 4 times d star Cp of Z L2 norm squared by Parseval again. And the reason I'm writing it that way is because I want to use the fact that C is monotone in its subscript. It's a generating function with that variable, so with non-negative coefficients. So it's monotone, and I can replace it by Cz hat, which is just 1 over 1 minus d hat. And so what I end up with is 4 to the power 4 times d hat over 1 minus d hat L2 norm squared. But that was exactly the integral that showed up in the proposition that was proved using calculus. So this is less than or equal to 4 to the 4 times beta. All right, so I'm not going to do all of the estimates for you, but you can do the same thing for the L infinity norm of H. In fact, it should be easier. So similarly, the L infinity norm of H is less than some constant times beta. And so you can substitute that in here. This term will be of order beta, because this ratio of the geometric series is bounded by the sum of the L infinity and the L2 norms, and those are both order beta. So this will be dominated by its first term, order beta. Beta is as small as we want it to be. This is order beta. So we get, finally, that F1 of Z is less than or equal to 1 plus, not 1. Yes, 1 plus order beta. And the order beta part is something that involves 4. All right, so it's some explicitly computable constant that depends on this 4 that was in the hypothesis here. And if you put some other number, then that other number would pop out. Now, actually, what got shown here in this argument was a little bit more, because this inequality that we used here would apply also if we had a k instead of 0. So in fact, these estimates that we were doing tell us that pi hat z of any k is order beta under the hypothesis that f is less than or equal to 4. So that will be useful. All right, so finally, the idea of the proof that F2 of Z is less than or equal to 1 plus order beta. I won't go into complete detail here, but you can get the idea from the following. So I need to look at the ratio of g hat of k at z and c at this partner value p of z hat of k. I need to show that the absolute value of that ratio is less than this number a, which is a little bit bigger than 1, as close to 1 as we want by choosing beta sufficiently small, under the hypothesis that that it's less than 4. So what is this? We have expressions for the reciprocal of g hat. It's 1 minus z omega d. Well, it's what we called f hat. Let me just write it that way. F hat z of k was, by definition, the reciprocal of g hat of k. And c hat is something explicit, and it's the reciprocal, really, that it's 1 over something, and what it's over is 1 minus p of z omega d hat of k. So I need to show that the numerator and the denominator are close to each other uniformly in k. All right, so we have to do a little bit of calculation here. We want to show it's close to 1, so let's factor out a 1 and write it as 1 plus whatever it needs to be in order to be correct. So that would be 1 minus p of z omega d hat of k minus f hat z of k divided by f hat z of k. This is just the same formula as we had before, except I've added and subtracted 1. I added 1 here, and then I subtracted 1 with this ratio. So that's true. And if you remember the way that we defined p, we had an explicit formula for p in terms of pi. Yeah, d hat k was the simple random walk thing. So you should think of d hat of k. D hat of k is the thing that we really understand. For nearest neighbor model, it's this thing. It's also sitting inside f. So f hat z of k is 1 minus z omega d hat of k minus pi hat z of k. So if you write down that this is what f is, and then you do the arithmetic in the numerator, the 1's cancel and some other stuff cancels. And when you look at what remains, you have minus pi hat z 0 d hat of k plus pi hat z of k divided by f z hat of k. And, well, that's just arithmetic. And no, so yeah, I guess I got sidetracked there. So p of z is z omega plus or minus plus pi hat z of 0. That's the way it was defined. So now we're using the fact that this is the good p. So that's why various things canceled, like the z omega d hat of k here canceled the one which is in the f hat. And what's left are these terms that I've just written down. And I want finally to write this in this form, which hopefully will remind you of something. So I guess that's just arithmetic. What did I do? I added pi z hat of 0 and subtracted it away there. And then the numerators match up with each other. So I want to show that this big fraction is something which is of order beta. And then we're done as far as f2 is concerned. And well, the argument for f3 kind of works the same way. The thing to be worried about, though, is that as z is getting closer to zc and k is getting closer to 0, this denominator is going to 0. So that's kind of a dangerous thing as far as showing that the fraction is small is concerned. And we have to be sure that when the denominator is going to 0, that the numerator is going to be going to 0 along with it and cancel out that potential divergence. The numerator is small anyway, so that's good news. The numerator is just small because pi is small. So here, all of this argument essentially was showing that pi hat of 0 was small, but as I was trying to convince you of a few minutes ago, that exact same argument shows that pi z hat of k is small for any k. So this is small, d hat's less than 1, so this is less than 2. This is small, that's small. So the numerator is small, so as long as the denominator doesn't do anything like getting close to 0, then we're okay. However, it will be getting close to 0 sometimes, and we need to concern ourselves about that. So first observation about the numerator in this fraction. We want to show that this is order beta. The numerator is order beta by the argument that we used for F1. But we can do better than that, because, and this is where F3 comes in. So I haven't used F3 yet. This is the one and only place where it gets used, and the price that we have to pay. I mean, so here we have to assume that F3 is less than or equal to 4, and then the price that we'll have to pay is to show that it's actually smaller than that later on. That's the part I'm not going to show you, but it's more of the same. But by making that assumption on F3, we're controlling the 1 minus cosine, which is in this difference between pi hat of 0 and pi hat of k. And with that assumption, we can show that this is actually a small multiple of this 1 minus d hat. So using F3, the numerator is also bounded above. Let me write a correct formula here. Yeah. Order beta times 1 minus d hat of k. So the first term there is obviously of that form because I've been saying that this pi hat is of order beta and there's a 1 minus d hat which is just sitting there. This is the k squared term, right? As k goes to 0, it's going to 0. This is clearly equal to 0 when k is equal to 0. And the thing is that you can absorb that into the 1 minus d hat by using that assumption on F3. So finally, for the denominator, the denominator is just what came out of the Lace expansion. So the denominator is 1 minus, well, let's write it as fz hat of 0 plus fz hat of k minus fz hat of 0. So f, remember, is the reciprocal of the Fourier transform of the two-point function. And when we put k equals 0, that's giving us the reciprocal of the susceptibility. So it's fz hat of 0. And then we've got our formula for f there. We do the comparison. This is what we get. And right. Yeah, but I don't think I want to do that. Yeah. I don't think I want to do that. So I want to look at, there's two cases. I want to look at z less than or equal to 1/2 the simple random walk critical value. Because in that case, there's no problem from this. This stays bounded away from 0. So in this case, fz hat of 0, which is 1 over gz hat of 0, is actually greater than or equal to 1 over cz hat of 0. So this is just saying that there's more simple random walks than self-avoiding walks. So this is this is a bound that you can't use if you want to go all the way to the critical point, but here we're staying away from the critical point even for simple random walk. And this is something explicit. In fact, this is 1 minus z times omega, and this is greater than or equal to a half. So this whole thing, in this case, so the denominator is greater than or equal to, actually I don't need any absolute value signs there. It's greater than or equal to 1/2 plus 0. This is non-negative, and this is order beta. So worst case, order beta, it's greater than or equal to 1/4. And so the case of small z is not really any problem. The numerator is small, the denominator is bounded away from 0, and so the ratio of the numerator and the denominator will be order beta, which is what it is that we needed to show. Case 2 is the more dangerous case. So when z is between 1/1/2 of the simple random walk critical value and zc, then when k is equal to 0, the denominator is going to 0, so we have to make sure that that gets canceled by the numerator. And in this case, we don't get any help from this term, which is vanishing. So the denominator in that case is greater than or equal to 0 from this term. But here we do get some help because this is not disappearing on us. This z times omega is at least 1/2. That's the situation that we're in here. So we have plus 1/2 1 minus d hat of k. And then we use the bound on f3 to tell us that this difference between f0 and fk, pi 0 hat and pi hat k is bounded above by a small multiple of 1 minus d hat. And so altogether, we get something which can be controlled by this term. So we had the factor 1 minus d hat in the numerator times something very small, and in the denominator we have a constant times 1 minus d hat. So it's a lot of estimates, but it has done the job in the end. So what this has, the conclusion that we draw from all of this is that f2 of z, under our assumption that it was less than or equal to 4, is actually less than 1 plus order beta. So I've shown you how to draw the conclusion that we need for f1 and f2 in order to verify the hypothesis of the lemma. There was also a f3 that we need to worry about. For f3, you do this again, but a little bit more. So f3 is more of the same. And that concludes the verification of the hypotheses of the lemma, and the lemma was sufficient. Yeah? Yes? That's right. Well, it is true because ZC is actually equal to 1 over 2d plus 1 over 2d squared plus higher order terms. And so if you take d big enough, this is less than any multiple of 1 over d. Right? That's right. That's right. Yes? I only used it here. It only got used at this point. So it got used at the point where we said, I've got this pi 0 minus pi k, and I have to absorb it into the 1 minus d hat. That's essential. And the only control I have on pi 0 minus pi k involves this 1 minus cosine of k dot x inside an L infinity norm. And that's what gets controlled by f3. So Bridges and Spencer did not do this at all. I would claim that this is actually a totally different approach to what Bridges and Spencer did. They did an induction on the memory. So they approached the self-avoiding walk by self-avoiding walks that remember to be self-avoiding over time span tau, and then they want to study n-step self-avoiding walks. So if they're able to control bounds uniform in the memory, they can take tau equal to n, and then it's just a self-avoiding walk. So they, of course, they have the pi of 0 and the pi of k and all of that, and they have to control these kinds of differences. But it's really an induction on the memory, and it's using complex analysis. It's a rather different approach.
Instead of looking at the pi hat 0 minus pi hat of k and bounding it in Fourier space, what they did was bound that in terms of a double derivative with respect to k, which gives spatial second moment.
Exactly. So what they did was they said that this is approximately equal to, this thing. And so they did study these derivatives, which are bringing down an x squared. So it's looking at the sum over x of x squared times pi of x. And in fact, this innovation, which looks at 1 minus cosine k dot x rather than k squared times x squared, is a good innovation. Yes? Well, you don't. You have to write down. You have to write. I can't say any intuition. You write down what F3 is, and it looks like this stuff again. I had hoped to say a few more things, but I see that I have a 2.25 minutes left. What I wanted to say more about was extensions of this. So this, what I've told you about in the LACE expansion, I'm not going to talk about the LACE expansion anymore in the remaining 2 lectures. Instead, I'm going to be talking on tomorrow about integral representations of the self-avoiding walk, which are then used, as I'll explain on Saturday, to study the 4-dimensional problem using a renormalization group approach. But there's a lot more to say about the LACE expansion because it applies to many other models. So I'll just maybe in the time that I have mention what they are. So there's percolation in dimensions above 6 for spread out models, oriented percolation in dimensions above 4, contact process in dimensions above 4, the easing model in dimensions above 4, lattice trees and lattice animals in dimensions above 8. There's connections with the integrated super Brownian excursion and super Brownian motion, things that Le Gall was talking about in his course some weeks ago. More recently, there's been work by Remco van der Hofstadt and Akira Sakai and Heidenreich and Longqi Chen in Taiwan on looking at long-range models. So if instead of having a self-avoiding walk, which is only allowed to step inside some large box, like I've been talking about here, suppose that it was allowed to take arbitrary long steps, but the weight of such a step would be inversely proportional to the length to some power. So maybe the d of x would be behaving like 1 over x to d plus some alpha, where alpha is potentially less than 2, in which case you have no variance for your underlying random walk distribution. And just to mention one example of a theorem here, Heidenreich has proved that the critical dimension for this model is actually 2 times alpha, which can be as small as you like. If you take alpha less than a half, alpha is anything positive here. If you take alpha as less than a half, that would be less than 1. So you would get results in 1 dimension. And what they've proved, or what he has proved, is that if d is less than 2, then the scaling limit of the self-avoiding walk with this kind of a step distribution for the underlying random walk is an alpha-stable process, as long as the dimension is greater than 2 times alpha. Okay, I think I'll stop at this point. Thank you very much.